I only now, after making the previous video, realize that it should have been Kinematics 0 here, but I didn't do too much. This is the video where we're really going to get into these pieces, and I'm gonna, for lack of a better word, lecture about what we should have learned, what we should have seen throughout those simulations, the explorations. These are kind of the rules that we're going to go into for how the graphs connect with each other. So the first thing that I want to do, I'm going to draw out some graphs. I'm going to make an effort to make them a little bit pretty. Let's scroll up, get some horizontal lines going here. So I'm going to have this graph on the bottom be our acceleration. And we'll notice that the units are meters per second squared. Sometimes my handwriting is awful on the slippery screen. Acceleration units of meters per second squared. Our position up top, which will have units of meters. And notice I'm using these square brackets to mean these. How I would formally say this is, let's say I have some function of time, my position. The units of the position are meters. So these angular brackets tell you units. That's kind of the association that I use them for. So when I'm talking about velocity, in SI, the units of velocity will be meters per second. We'll notice a trend that we pick up a per second each time we go down. So when I did a meters per second and I took a per second, dividing by fractions is like multiplying by the inverse. And so that's where we get the second squared in the denominator. There will be a strong reason for that in just a moment, and for why we go backwards the other way. We multiply by a second every time we go up. So we've got all these pieces are going to be graphed with respect to time. We won't always have time on the x-axis, and x-axis is going to be a weird thing. It's one of many reasons why I'll use the letter S for position and not X or P or something like that. We'll get into why, but just so you know, I'll generally call this a position of time. S of t is the function, V of t, and A of t. So when we're graphing any sort of motion, we can describe them using these three. And I would say technically, any one of them is kind of the most important, but this one carries the most information. Because we might have seen, if we did careful exploration before, maybe we had a velocity where we started from rest and then we sped up in the positive direction. Well, this graph will always correspond to a graph down here where we have a constant positive. And this is because this graph is telling us about the slope of the graph above. And when we look at the slope here, we can see the slope is this constant positive number. So that's why we have a constant positive down here. If I'm being really formal about it, I should maybe draw this with a straight edge, some constant positive number, which came specifically from this steadily increasing velocity. But if I were then trying to say, okay, what motion described this graph on my position graph? Well, there's going to be multiple correct answers. We could have said, let's start from the wall. And then we slowly pick up speed, and eventually our graph kind of looks like this. But we could have also started from the starting point, or really anywhere else. And the rest of the shape of the graph would be exactly identical. Now, why that is going with that rule that I snuck in below. When we were looking at this graph, the graph above it, we take the slope of that graph to figure out about the graph below. So when we were looking at the velocity versus time graph, the slope was a constant positive number, giving us this constant positive number down here. But here, when we look at the slope, and I recommend do this with your pencil, do this with your finger, you can see the slope is flat at the very beginning. That's why it's 0. But then as time goes on, the slope slowly increases. That's why it went up a little bit here, but then when we check back a little bit later, the slope at this point has increased further. When we check at these various intervals, the slope is steadily increasing. It's going up and up and up as time goes on, which if we've done our calculus, we're going to recognize this idea as what we call derivatives. But it still works in the idea of slope, especially when the slope is constant or when we're just looking at one specific point. We'll eventually come up with equations using both calculus ideas and the geometric ideas that mean the same thing, because slope, there's a couple ways of defining it. At its very rudimentary level, you're explaining slope to somebody who's seeing it for the very first time. This third or fourth grader, they're being taught about slope. What will we tell them? Well, we say, it's like rise over run. Between any 2 points, if you compare how high the rise is with how high the run is, between any points of the same run, we see we have a higher rise, if I can spell rise, as we go further along. And the calculus idea is just taking this to a limit. It says take the limit as this run shrinks. As I take this rise and I bring it closer and closer and closer and closer so that you get the instantaneous, that tangent slope, the slope of that tangent line. But if you were doing something like this, that's the same slope, whether we did 2 points that are far apart or not. So even with only the algebra technique, we can still do this, but we'll also be able to, when we invert this relationship and figure out kind of what the quote-unquote opposite of slope is, we can figure out the other pieces. But this is one of our 2 fundamental rules, that if you want to know about the graph below the graph you're looking at, take the slope. And in calculus, we write this using the language of derivatives. The derivative of the position is the velocity. And this would technically be position as a function of time and velocity as a function of time. This works at every single point. But the algebra-based version of this is just saying the slope of the position tells you about the velocity at any given point. This still helps us build sketches, figure out ideas, do that sort of stuff. And it works going down the graph ladder. If you wanted to know about the acceleration graph, well, that just means you take the slope of the velocity graph. Saying the slope of the velocity graph is the acceleration graph. And we could go down the graph ladder further. The slope of the acceleration graph is what we call the jerk. It's just that this isn't as useful of a thing. The position tells us where we're at. The velocity tells us how fast we're going. And the acceleration is actually kind of this unintuitive thing, but it will fundamentally be related to forces through Newton's second law, as we'll eventually find. The force is equal to mass times acceleration. At some level, there will be more details, but that's kind of the link here. You can talk about jerk, it just often doesn't have really meaningful context. So that's our recipe for going down the graph ladder. We just have to take the slope. And circling back to that thing that I started at the beginning, if I knew this graph, we could figure out what a sketch of the graph above had to look like, because we could say we start with a slope of 0, and then as time goes on, that slope gets steeper and steeper. We go from this t to the 0th power, which is a constant, up to a t to the 1st power, which is a line, something that looks like y equals mx plus b. It's just that in this case, the slope was a constant related to our acceleration. The b was 0 because we started from rest. And quote-unquote x is taking the role of t, the x-axis, the horizontal axis. And quote-unquote y is taking the role of our velocity. But this still is going to look exactly like that, and we'll circle back to that idea. The other idea is that this one above it, a lot of people like to say, oh, this is like exponential. It's not exponential. This is a quadratic, and it's why we were so obsessed with quadratics back in like Algebra 1 and Algebra 2. because when this looks like some sort of ax squared plus bx plus c, it's just that these have different roles. What we find is that this is the core part of it. The how quadratic-y is it, and what's our initial slope at the origin? In this case, the b is 0 because we started at rest. And we'll get, again, more into that in a little bit. But this plus c is sort of this free parameter. We have the same slope at every spot. When I look at this spot right here, this slope is the same as this slope. We could have started from any initial position. That initial condition, this plus c, was arbitrary. It helps us define where we start from or where we're modeling, but the rest of it is kind of this core contents. So we actually need more information, more contextual information and or assumptions to go up the graph ladder. Versus going down the graph ladder, we have perfect information. So if you knew the position graph, you can fully define these two. But if you only knew this one, you're going to have to know some extra context and or make some assumptions when you go up the graph ladder. There's always going to be that extra parameter. And that's what we're getting at when we invert this relationship. If we're saying that we have a rise over a run that equals a thing, well, then I could take whatever thing that is, multiply by the run, and it would get me the rise. This would mean that the change in the graph above has to equal the run time, so this delta t, times the value of the current graph. But this only works under the assumption that the value of the graph stays the same, like for our acceleration. This idea works perfectly if I just want to say, well, okay, if I let this run for, let's say, 10 seconds, or in general, some sort of delta t, well, then I'm taking that delta t times whatever that a is, and what I'm doing there is I'm taking this dimension, the acceleration, multiplied by this dimension, this seconds. And so when I take that acceleration times that delta t, when I take meters per second squared and multiply by some amount of seconds, there's some cancellation, and we end up with some meters per second, with a change in the velocity. The more fundamental idea here is the area under the curve. This corresponding area tells us how much the graph above us went up or down, how much it changed. A positive area means it went up. A negative area would mean it goes down. We'll look at that eventually. But that means that when I look at this equivalent 10-second or equivalently delta t mark, the graph went up some amount in that time. But that rule wouldn't work going up here to here if it was just the value times the time. Because if I took 0 times the time, oh no, it didn't go anywhere. That's not true though. We see that in the graph above, between, if I erase some of this junk, maybe redraw it, we did have some sort of change. We moved forward from our starting point. And if we just did 0 times that delta t, we don't see a flat. We see it's locally pretty flat because we don't have a lot of area under the curve. But as time goes on, we accumulate more and more area per next chunk of time. And in any way we want to describe it, we could do this with our calculus techniques, but we also could do this algebraically, where we figure out here, area of a rectangle is super easy. It was this height times this base. But now up here, it's a triangle. We have to do 1/2 base times height. And when we use that tool, that's where we start getting these equations that look crazy. They look like they came from nowhere, where we say, well, in constant kinematics acceleration, we start with an acceleration of t just equals a constant, a. It could be any number. It could be 0, 1, -10. But a, this algebra, just represents a number. So when we go up and we try and recreate the velocity as a function of time, by taking the area under the curve, what we're doing in the very formal language is we're integrating, taking the area under the curve of our acceleration as a function of time with respect to time. Now what that means, geometrically, is we were just taking that acceleration times that change in time. But in general, what this could mean especially if we think about it through the lens of delta t equaling t final minus t initial. And we call t final just t, and t initial or t naught. N-A-U-G-H-T. This is like not and dreadnought. It means nothing. You dread nothing. You start at nothing, not zero. That's why it's like, oh, it's the 1910s. It's the 1970s. It's the 2010s. It's the 20... Wait, what are these? These are called the 20-aughts. It's that same A-U-G-H-T, or sometimes called the 20-noughts. Just an etymology thing there. But anyways, if we use that relationship here, you would get AT, and then distributing the AN, you get minus an A times a T naught. This sort of term we think of as a plus initial velocity, a V naught. Again, because you had that parameter where it didn't matter where you started. The slope of this line is determined when we look at this from the perspective of y equals mx plus b. The b tells us about the initial velocity, but the initial velocity has no impact on what the acceleration is, what the slope is. And so we end up with a formula that looks like this. If we check out our equation sheet, especially looking at what we call the Suvat equations, this means it's like an acronym essentially. T is for time, A is for acceleration, V is for velocity, U is for initial velocity. I will often call it V naught in these contexts, but when we get to especially collisions, when we're conserving momentum, we'll have a lot of different V's going around, and that's where it will become useful for us to distinguish them with different letters, which will of course confuse the Romans, because to the Romans, U and V were the same letter. And S is for position. This is kind of why we call that. I mean, I guess we could have called it like Puvat for position, but there's a lot of reasons why we choose S, so that's a convention that I will use. So I will use S of t equals, and again, if you go through and geometrically draw out this diagram where you treat it like you have a constant acceleration times time and you build a generic delta t, if you do the same thing for your velocity as a function of time, where you draw it out as I have a generic v naught and some sort of corresponding slope, if I calculate the corresponding area and some equivalent delta t, what we'll find is we break it up into two chunks. A rectangular chunk where we have v naught times delta t, and you'll add this extra chunk here. You've got like this final velocity minus the initial velocity, and then times delta t again, but final velocity is this whole equation. When you plug that in, you stir the alphabet soup, which we'll do a little bit more of in class. I just don't want to show it right now. We'll find that this will simplify into 1/2 at squared plus v naught t plus plus a initial velocity, initial position. There's like 400 texts going on, and my mom is currently in the hospital. Everything's fine, but I'm just distracted. It's okay. And it also doesn't help that t looks the exact same as plus. I try my best to kind of separate those out. S naught, it's an initial position. It doesn't matter where we started from, but our initial velocity and our acceleration will dictate some of those pieces. And to show you a little bit more about what those look like, I'm actually going to go to Desmos and teach you all a nice, neat trick. So let's go to Desmos graphing is usually what I go. It's the first one. So I'm going to type in exactly what I just found, that my position as a function of time is equal to 1/2 times my acceleration times time squared plus a v naught times t plus an s naught. And I'm going to add a slider for each of those things. The s naught slider controls where I start. It moves the whole graph up or down, shifts it, a vertical shift. I could start at the origin, or I could start 10 feet behind or whatever. I could start ahead. It's relative to whatever reference point we choose. This is our initial position. versus the initial velocity, this is usually the one that's hardest for us to figure out, this plus b thing in the middle, because again, this looks exactly the same as, like, I'll use capital letters, ax squared plus bx plus c. This looks exactly the same, where the c we understood as that y-intercept, that vertical shift. A was what we called the concavity. 0 just makes it a line. But then any positive number makes it concave up. Any negative number makes it concave down. And then we're like, B does something weird that we don't understand. Well, we didn't understand it because we didn't have calculus. We didn't have this context where V naught, the thing that controls this B term, the thing on the t to the first power times t to the 0th power over here, the 0th power is just saying this is a constant. The first power is saying this is a constant times t to the first power, and this is our quadratic term. The constant, in this case it's 1/2 a, equals our capital A, thinking about it in that context. But this V naught, this B term, was always this like, it's this weird thing that does this weird behavior. But now we have context to understand it. If we start from rest, then our slope of it is flat. It's 0. We're not moving anywhere for just a moment. But if we started moving, we'd have to start with a positive slope. And if we start moving faster, we'd have to start with a much more positive slope, which of course, mathematically, geometrically shifts the parabola over in this weird way that previously was hard to understand. But now if we understand things like, okay, I'm going to start from above, but I'm going to have a small negative curvature, and I'm going to start moving forward. But as time goes on, because of that negative curvature, I stop, I turn back around at some point when my velocity is 0, when my slope is 0, and then I go backwards and I hit the origin at some point. This is what we'll do a lot when we throw objects up in the air. Maybe I threw it from my hand. I threw it up, and I'm 4.7 Blorgelflarbs tall, and I throw it up at some speed of 2.5 Bliffelbobs. Well, eventually we can figure out how high up it went in terms of whatever units we plugged in. In this case, I made up crazy nonsense that I probably will have something different if I came up again. But we could then figure out where and when it hits the ground. Or conversely, the other route would be if we instead threw it from ground level. It will give us more information about, like, well, how long would it have taken for it to get to where I actually threw it from? And this extra context, like, now we have a reason to care about all of these things, about finding maxes and mins and vertexes, about finding y-intercepts, about finding roots. Physics gives us a reason to care about all of that stuff that we kind of did math for math's sake back in algebra and trig and geometry and probably calculus. So this is kind of where things come back together. If all of those math demons of math past are coming back to haunt you, those vengeful spirits, this is where we get to turn them into helpful ones by really re-understanding what those pieces are, how they do, why we care. We now have a reason to care because these simple rules of understanding how the slope takes you down the graph ladder. So position, velocity, acceleration, all versus time. Slope takes you down, and area under the curve takes you up. With this extra caveat of you lose information when you take the slope. You have to gain information using some context, what we call boundary conditions, often initial conditions, to figure out, oh, there's this plus c parameter. Those, for the Suvat equations, are these simple things that we developed here. And there's another one, which we'll go into in a little bit, but it's basically v squared equals v naught squared plus 2a delta s. There's some restrictions on when you can use this beyond just the assumption that there's a constant acceleration. That's the other thing. Suvat is really an acronym for constant acceleration kinematics equation. Which is why we often don't write that, we write suvat and say suvat because it's way faster than this. We'll come into where this comes from in a moment, but basically all of these things reduce to, what if I had zero acceleration? If I plugged in a 0 here and I plugged in a 0 here, well, then this whole term goes away. And then this whole term would go away. And it reduces to stuff that you can recreate in your simulations. If you have a 0 acceleration, then your velocity will just be a constant. The acceleration will also be a constant, just a special constant, 0. And then your position function won't be a parabola anymore, it'll just be a line. And this one also would update. You'd have none of this term. You would finish, your final velocity would be the same as your initial velocity if you have no acceleration. All of these tell this consistent story through these rules. And these equations didn't just come from nowhere. I know when I took this class, it really looked like this equation came from nowhere. S of t equals 1/2 at squared plus v naught t plus s naught. Like, this is so many things. Your typical human brain only has 4 to 7 chunks of working memory, half of which are usually consumed by frustration, anxiety, poor mental health. Meaning, when I look at this thing, which is like, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bunches of stuff, this looks enormous. So how is it that I can just rattle it off like, it's just 1/2 at squared plus v naught t plus s naught? A, it's because I've done it a bunch of times, but B, it's because I understood the underlying structure. I happened to be taking algebra-based physics at the same time I was taking calculus, which gave us that reason to really understand these simple rules of, okay, power rule this to get to, you multiply this thing times t, and then you add a plus c, but the plus c in this context has to carry the same units as velocity, so we call it an initial velocity. And then you do the same thing. Initial velocity times time plus your constant plus the rule for how you do power rule is you make sure you do, if this is to the first power, you increase the power on the t, and then you divide by the new power. So we divided by 2 and increased it by 1. Well, that's the same thing that we can get through a little bit more complicated means of the area under the curve and storing up alphabet soup. But the geometry rules from algebra, those do the exact same things. They get us to, if I have a constant times a time, in this case we usually say let's start from 0 and go to t, well then the length of this rectangle is t and the height is a, so a times t tells us about a change in the graph above, and the graph above will always equal a change plus where you started. So when we plug in a times t, we get that. And you can do the same thing when you say, well, s of t has to equal initial position plus a delta s, but delta s is just the area under the curve of this thing. Well, then when you draw that out, you get that initial velocity drawn generically as some positive number, and you do this area of the rectangle plus this area of the triangle, you stir the alphabet soup, it becomes this. It didn't just come from nowhere. Physics equations don't just come from nowhere. We didn't just pull them out of our butt. They were developed and made for a reason, and then we can further go and test them against other situations and see that they build consistency, unless there's something wrong with our fundamental assumption, which could be something more fundamental about how the universe works. It could be something about maybe we didn't quite measure the acceleration precisely enough, or something like that. But the physics equations fundamentally carry this structure that describes all of these different things, and we're going to get more and more used to it as we start playing with these equations, especially plugging them into different situations. So that's the next thing to throw us into, is we'll start off going into these pieces where we are describing these pieces using these rules that we've just found about how to go up and down the graph ladder, and there will be more with accelerations on our first homework as well. But this is kind of that first thing that I want you to do. It's called constant motion homework. I'm probably going to rename it to constant motion activity or maybe homework 0. But there's a bunch of things that we'll get practice with and we'll debrief on in class. I think that's all I want to cover in this video. I think that's a good start on our kinematic stuff, but it will keep coming back up. Forces and kinematics, and system schemas, they'll all come back to roost together and help us build a model that helps us describe the world around us.